Hi everyone. So welcome to Design and Analysis web series. I have posted so many concepts related to design and analysis algorithm like recursive and non-recursive algorithm, greedy algorithm, dynamic and so on. So if you want to know more about this, kindly subscribe and follow. Hi everyone. Welcome back to Design and Analysis of Algorithm series. So already we have completed the recursive algorithm factorial value example. So today also we are going to see another example using the recurrence relation, and we are going to solve that recurrence relations. Example 2, we are going to see number of binary digit in n's binary representation. It means nothing but we are going to count the total number of digit in a decimal to binary conversion. So how many total number of digits are there in the conversion after the conversion of decimal to binary? So here we can see one example by conversion. We shall take n is equal to 3. We want to convert this n is equal to 3 decimal value into binary. So usually how we will be doing? We will divide it by 2 and we'll get the remainder. So what is the value? 1 1 base 2. So totally how many digits are there? 2. So 2 is the total number of count after converting the decimal value into the binary digits. So how we will be doing this one? Just we are dividing the n by 2. So how many value we are dividing? So how many value? So n is equal to 3 na. So n is equal to 3 means that is the n value given, and we want to convert it into binary. So if you want to convert it into the binary, we have to divide it by 2. So plus 1 is nothing but to increase the count. So first time I have counted, and recursively again you want to call the algorithm n by 2. So n by 2, suppose again recursively you want to call a binary 3 by 2. What is the value? 1. So 1 plus 1. So when n is equal to 1, what is the return value? 1. So there is no need to do any addition if the value of n is equal to 1. Therefore 1 plus 1. 1 is nothing but it is a total number of count, 2. So 1 plus 1 is equal to 2. So how many total number of digits are available in the conversion of 3 into binary? 1 1. So total number of digits is 2. So this is the recursive algorithm logic, and using this logic we are going to write the algorithm for binary digit representation and the total number of count available in the digits. So this is an example for conversion of 3 base decimal to binary 1 1. So okay, so when we convert the decimal value 3, we will be getting 1 1 as the binary value. So now we can write the algorithm. We know the logic na, so now we shall write the algorithm for binary digit representation and the total number of count. So what is the input value? N. So n is equal to 1, then what we need to return? 1. So there is no addition. So this is the base value. Recursive algorithm is nothing but calling itself. When it will stop calling itself? When it reaches the base value. Or else what we are doing? Just we are dividing the given number by 2, and to count, we want to count it na. So we will be having one addition, plus 1. So that plus 1 is nothing but we are counting the total number of digits. So for that we are adding plus 1. So initially we will be having 0. 0 means there is no more number. So definitely if your else part is achieved, definitely we are doing one count. Therefore we are giving plus 1 in the return part, else part. Okay, so in the else part, if it is returning n by 2, we are counting the 1 value. So what is the general plan? We will write input size n, second step basic operation. So what is the basic operation available in this binary representation? Addition. So how many times we are adding? n by 2. Recursively again and again we are calling this one n by 2 times. That is the basic operation. So third step is how many times we are doing this basic operation. Based on the n value, we are going to call the recursive algorithm. So the n is equal to 3, therefore twice we called the function. Suppose if it is 10 or 11, then it is more than 3 times. So now we need to find the recurrence relation. A of n is equal to how many times the basic operation? So a of n by 2. n by 2 times the basic operation is performed, plus to count the value 1. So we want to increase the count. So that's why we are giving 1. So we want to increase the return value. So nothing but it is a count value. We are counting how many number of digits. 2 digit, 3 digit. So if the decimal value is 3, totally how many digits na? 1. So this a of n by 2, what is the meaning? Total number of addition. How many times we are doing the addition operation. That is, and what about the initial value? A of 1 is equal to 0. What is the meaning? 0 means how many times you are doing the addition. So when n is equal to 1, we are not doing any addition. Just we are returning the value 1 and no more addition. No more count we are doing. That's it. Finish it off. So that's why initial condition is a of 1 is equal to 0. So a of n is equal to a of n by 2 plus 1 is the recurrence relation, and a of 1 is equal to 0. So now what we need to do? We need to solve this recurrence relation. We shall write the first equation, n by 2 plus 1. This is the first equation. We shall consider this as a first equation. So using substitution method, we need to find the value for a of n by 2. So a of n by 2 is equal to, we need to apply n by 2 in the place of n. Already by 2 is there, plus 1 is there. We need to keep it as it is. So therefore a of n by 2 squared. So already 2 is there. So now again we are applying n by 2. So already 1 is there, that one. And then after substitution we will be getting another one. So therefore we will be getting now plus 2. A of n by 4 plus 2. This is the second equation. Either we can write it as 2 squared or we can write it as 4. No problem. Both are same. Now we need to find the a of n by 4. So a of n by 4, what is the value after the substitution? A of n by, we can write it as 2 cube or 8. So 2 cube plus 3. So how we are getting 3? Already 2 is there, and in the first equation we need to substitute the value so that we will be getting 1. So 2 plus 1, 3. This is the third equation. Suppose if you are getting next equation, definitely it will be n by 2 to the power 4 plus 4. So now by having this one, we can define the general term. The continuation, we understood the continuation, how we are getting. Therefore we can write the general term as a of n is equal to a of n by 2 is common to all the equation. So we shall write it as a 2, and the power can be represented using the variable I, where this I is represented as 1, 2, 3, etc. Therefore 2 to the power of I plus 1, 2, 3 na continuation. So 1, 2, 3 can be represented as I. So this is the recurrence relation general term. So now we need to solve this recurrence relation. So n is equal to 2 to the power of I. So how we can write it? Using the initial condition. What is the initial condition? A of 1 is equal to 0 na. Therefore n by 2 to the power of I is equal to 1. So n is equal to 2 to the power of I. Wherever n appears, we can substitute it as 2 to the power of I. So a 2 to the power of I by 2 to the power of I plus I. So now a of 1 plus I. What is the initial condition? 0. Initial conditions of 0 plus I. I can be represented in the form of logarithmic. So both the side we can take a logarithmic value on both the side. So log n is equal to log 2 to the power of I. So I log 2. So log n this side. So I is equal to, we can bring this log to this side. Therefore it will become base 2. So I can be written as log n base 2. Log n base 2. So this is the time complexity for binary representations of conversion of decimal to binary to count the total number of digits in the binary conversion. So this is the time complexity for binary digit representation. We are counting the total number of digits after the conversion. Thank you.